So really, we've been talking about some pretty simple piping configurations in our pump system so far. So we've talked about these fixed speed pumps, driving chiller load, and sending it out to the zones with either a 2 or 3-way valve, but really a lot of our systems may look more like this configuration. And this is what we call a primary-secondary configuration. And it's very common to have the secondary, which is on the distribution or load side, to be variable speed with a VFD. So there's 4 main characteristics that make this a primary-secondary system. So the first one is these fixed speed plant pumps. So associated with each chiller or boiler or your equipment in the plant, you have a dedicated pump that's operating a plant loop. You have separate pumps for the distribution side, and often those will be variable speed, as we'll see momentarily. You'll have some type of load control that'll tell those pumps, if they are variable speed, what speed they need to be running at to meet the load. And then most important is this hydraulic decoupler or bypass in the plant. So what this does is hydraulically separate the loops so that you can run them from a flow standpoint isolated from one another. So why do this? Well, there's a couple of benefits. The first one is that large pieces of equipment that aren't as tolerant of flow variations can be very happy with a fixed flow through the equipment, and for boilers and chillers that has a certain amount of equipment protection to it. But at your load side, which will often vary, now you can have your pumps turned down to get some of those brake horsepower savings that we talked about last time, and even reduce some of your thermal losses associated with running more flow than you need through your system. So let's see what that looks like in practice. Well, at full load, you might have a situation where your bypass isn't leveraged all that much. So where you have your valves at the load side 100% open, full flow, you're at your design condition, your distribution pumps are at 100% speed. That gets sent back to the plant, and the chiller, in this case equipment, will run at full load to put out its chill water supply set point at the primary loop that will then be taken up by the distribution pumps and sent to the secondary loop, or the distribution side. But things get to be a little more interesting at part load. So here, we might have the control valves at the load side throttled, in this case 75%. So you're outside of your design conditions, which in most buildings is going to be most of the time. And here the distribution pumps are able to turn down, able to provide less flow to meet the reduced load at the coils. But the plant is still getting the flow that it requires because of the bypass. So that decoupler there is going to be a short, fat piece of pipe. Might be 10 inches long, very wide diameter relative to the rest of the loop, and that's essentially a zero pressure drop. So when those chillers need flow, they're going to get it in a recirculation loop right at the plant. So as the load drops off further, maybe one of your air handling units turns off, or you have a completely closed control valve, then your plant equipment might start following suit, but it's still getting the flow that it needs. So in this case, you only have 250 GPM needed by a single air handler, but the chiller can maintain its 500 GPM with its constant flow pump because of the bypass and because of the decoupling. So we have to be careful with a little bit of added complexity here. Adds a little bit of vulnerability when things start to go awry. So here's an instance when you look all the way to the right, you have no load at that air handler 2, but the valve is 100% open. Why might that happen? Well, you might have a valve that's stuck 100% open when there's essentially no load going across it. Or, what might be more common, is you have a valve that isn't being told to close when the space is unoccupied or an air handler is not in use. So if the air handler's off, there's no airflow going across the coil, but there's full flow going through the coil. Well, what might happen? So you can see here, there's a little bit of color gradient to try to guide us through this, is that you have some part load going through the first air handler, and you have full flow going through the second, and instead of having warm water coming back, you have this mixed mild water that's not only going back to the chillers, but now some of it is bypassing because it's more than the chiller needs. It's 750 GPM coming back to the plant instead of 500. So where does that bypass flow go? Well, now in that direction, it's going to mix with the chilled water supply. So you're not going to be putting out your chill water supply set point on the distribution side. So that air handler 1 is going to have its load increase and increase because it's not getting its design chill water supply set point. So this is an instance where, because we have this primary secondary system, when we have control sequences either not doing what we expect or perhaps not accounting for every control sequence that's possible, we might have a situation where this plant's going to be performing fairly poorly, and you might see some unhappy folks associated with that air handler 1. So another thing that we need to watch out for is where the bypass is. So that bypass, that short, fat piece of pipe that acts as a zero pressure drop to decouple the loops, that may be located inside your plant, as shown here, or it might be in a configuration where it is outside the plant. And what is the effect of those two options? Well, inside the plant is really what we want. It's going to allow the chillers to see the same temperature. They're going to share the load. There's going to be the same percentage of runtime and loading. And unless it's not designed to do that, you're going to have a situation when the bypass is outside the plant where you have different water temperatures going in. They're seeing different loads. The load is not shared equally. And cycling or turning down those chillers is going to be harder to do. So be aware of how bypass location may affect how the load is distributed. So seeing all this can be a bit difficult. So just to kind of add some layers of complexity, this may be more like what an actual system is that we're looking at. More complexity in the plant, possibly dual secondaries, in this case, being able to send out flow and get load to an ice tank, and multiple zone loads, not just 1 or 2 air handlers. You might have a whole slew of coils that you may be serving. So it can be difficult at times to kind of track what's going on, where the bypass is, and how this flow may be distributed. And one of the consequences of that is it may be difficult to see what pump interactions you may be having in your system. So we'll cover what that means. So pump interactions really come in 2 forms. So you can have pumps in parallel. So this is typical with redundant pumps, or where you have a common header that the pumps are distributing to. Or you could have pumps in series, so one after another. So they're designed to either increase flow or increase pressure in your system. But they're actually doing that. So let's take a look at what that looks like on the pump curve, and we can make more sense about how those may be operating in practice. So here's the head flow combinations that we see on pump curves, and based on the impeller size, we may have an operating point somewhere, hopefully near that peak efficiency. So if you were to put 2 pumps in parallel, so same pumps, putting out to a common head, is this where the new operating point is going to be? Are you going to get double the flow as the theory may indicate? Well, it depends entirely on your system curve of how much flow you're going to get. So in this case, being that that system curve goes through your original operating point, the system curve is going to continue, and where it intersects with that second impeller layered next to the original impeller is going to be what your new operating point is. So nowhere really near here, twice the flow. So very important as you're putting pumps in parallel, and if you expect to run them together to get increased flow, you want to go through an exercise like this to see what you're actually getting. Same story with pumping in series. So you may expect that you're going to get to that second or double head if you need more pressure in your system, but really what's going to happen is you're going to follow that system curve and intersect with the second impeller stacked, in this case, on top of the first. So it gets even a little more complicated when you have different size pumps. So let's say on the left here, when you're pumping in parallel, if this is your system curve for parallel pumps of different sizes, how much extra flow are you going to get? Well, in this case, you're not going to get any extra flow. But if you just move a little bit to the right there, so if you have a little pressure drop in your system, you're going to see this big change in flow, which is not really the type of operation we want to have out of our pumping systems. And same thing with the pumping in series on the right, is that if we're kind of right at the threshold of where you're going to register that smaller pump, then you're going to see these big changes in your system. You're going to want to be aware of effective pump curves. and the possible operating points depending on your system curve and how it may change to what actual combinations of flow and head are possible for your system. So it's also worth noting that as we have more high-performance buildings and additional systems, we might even have more complication to our primaries, secondaries. So this is a simplified flow diagram that came from a deep energy retrofit project where we had quite a bit. We had low temperature radiant in the zone served by stratified hot water tanks that had a sidearm heat exchanger served from solar hot water. There was gray water heat recovery that was preheating the water going to those tanks. And then there was a holding tank for the domestic hot water with return pumps, in addition to a booster boiler going to those stratified hot water tanks. So very complicated system. Hard to look at something like this and determine how it's going to operate. So one of the things that we recommend is trying to build these types of simplified system diagrams that we'll get into in later videos, and how you can more effectively recognize where you have problems. So based on that same design drawing, we realized that we had missing balance valves. We had essentially dual secondaries, where one of the secondaries didn't have pumps to do flow control, and also we had some of that pump interaction. So the design concept was to run the boilers and the boiler pumps together to meet full load, but when we looked at it on the pump curves, we were able to determine that we weren't going to get the full design flow through those boilers and out to the primary system as indicated. And then you may have some basic systems out there that might be overcomplicated and might have a primary secondary system that's not working well or not a good fit for that application. So here's a drawing that we had from a pretty simple hot water system, and the flow diagram that was on the wall as part of the as-built indicated this type of configuration. Rearranging the diagram slightly, we're able to see this typical primary secondary system taking shape. But a few things that we noticed: look at the secondary pumps, how they're noted as constant volume, and look at the flow requirement on the boiler versus the coil. Note the type of valve that's associated with the load, three-way rather than two-way. So in this system, what purpose does the bypass serve? So what we noticed is that in this case, because you had the same flow requirement at design conditions between the coil and the load, if there would have been a single pump or a single set of pumps sized to handle the head of the entire system, you wouldn't really need this primary secondary. And in fact, because the bypass was installed not as a short fat tube, there was actually pump interactions in this system as well. So these are the types of thought exercises once you can go into a mechanical room, look at the system diagram, understand the HVAC equipment, the heat transfer that it's trying to accomplish, and recognize these piping configurations, how it should be and how it could be. And with that, we're going to move on to airside systems, but first, look in the comments section if you're part of the RCX practicum for some exercises to practice what we've done with pumps so far, and then we'll continue with the rest of our HVAC fundamentals.